In today's lecture video, we're gonna talk about organic compounds. What are organic compounds? Why we need to study about the organic compounds and what are their properties? So let's get started. Organic compounds are the compound basically made up of carbon atoms. So those compounds that basically made up of carbon atoms we call as organic compound. And what is organic chemistry? Organic chemistry is the study of these carbon containing compounds, right? So let's see what's the difference between organic and inorganic chemistry, or basically organic and inorganic compound. So organic chemistry is the study of carbon containing compound, like I already told you, and whereas inorganic chemistry or inorganic compound is the study of element and all non-carbon compound. For example, NO2. So that doesn't have any carbon atom. And what's the special thing about inorganic compound? They are characterized by the presence of ionic bonding. So we're going to talk about what is ionic bond and which kind of bond we normally get in organic compound. So now let's compare the properties of organic and inorganic compounds. So the property is bonding within molecules. So organic compound form covalent bond, whereas inorganic compound form ionic bonds. So what is covalent bond? Covalent bonds are formed by sharing of electrons. Sharing of electrons. Whereas ionic compound or ionic bonds are formed by transfer of electrons. So let's take an example. If you have atom A and B, so they form a bond between them, right? So this bond is made by sharing of two electrons, whereas one of the electron comes from the A and second electron comes from B, and they just share both the electron. So this kind of sharing of electron we call as covalent bond. When in an ionic compound, the same two element, let's say A and B, this is their electron, respective electron, but let's say A donate the electron, A transfer the electron to B, and now this electron is on B. So this is a transfer of electron, and that's why they form ionic bond. So forces between the molecule, in organic compound they are generally weak, whereas in an organic compound they are strong because of the ionic bond. Physical state, the organic compound can be gaseous, liquid, and low melting point solids, whereas inorganic compounds are high melting point solids. They need more energy to get melted. Organic compounds are mostly flammable, whereas inorganics are non-flammable. The most important property is solubility in water. Organic compounds are less soluble in water, whereas inorganic compounds are highly soluble in water, right? The conductivity of organic compound in water solution, they are non-conductor. They cannot conduct electricity, whereas inorganic compounds can conduct electricity if they are present in a solution, right? And the rate of chemical reaction usually slow. Inorganic compound, they are fast. So they have differences between the different properties. So now let's talk about the bonding characteristic of the carbon atom. So we know carbon belongs to the fourth group of the periodic table, and so it has 4 valence electron. So I can say carbon has 4 valence electrons. So what does it mean by the valence electron? So valence electron are those electrons that actually take part in the bonding or to form a bond. So if carbon has 4 valence electron, so it can form 4 bonds. For example, this is carbon, 1 bond, 2 bond, 3 bond, 4 bond, and then you can have hydrogen across the bond. hydrogen. But if we go through the hybrid orbital theory, or if we talk about the orbitals and the arrangement of orbital within the carbon atom, we find that, so this is orbital, this shows. And what is orbital? Orbitals are the area within the atom where you can find the electrons. So, and each orbital can take up to 2 electrons. So if you can see, you have 1s orbital that already has 2, 2s already has 2 pair electron, but the 2p has 3 orbitals, 1 orbital, 2 and 3, and out of the 3, 2 orbitals consist of single electrons. So how many more electron this carbon atom can, or how many bond this carbon atom can form if they have 2 unpaired electron? So that means they can take 1 electron from other atom and 1 more electron from another atom or same atom. So by looking at this structure, we can say carbon atom can only form 2 bonds, right? Because each single electron get paired up once they form the bond with other atom. But like I already told you that carbon normally form 4 bonds, but how is it possible? So this is possible from the theory of hybridization, where it says so let's remove this. Let's understand what is hybridization theory. So during hybridization, one of the electron from the 2s moves from here to the up, and now they're gonna mix, all these 3 orbitals is gonna mix together. So after mixing, they normally going to form 4 new orbitals. There are 4 new orbitals, and these new 4 orbitals we normally call as hybridized orbitals, and they have equal energy, right? Like you already see over here in the previous, 2s and 2p has a difference of energy, right? 2s is lower in energy compared to 2p, but hybridized orbitals have equal energy, right? And then each hybridized orbital has 1 electrons. So how many bond this carbon normally form? So each hybridized orbital can take 1 extra electron to get a pair of electron. And how they're gonna get this extra electron? From other atoms, right? Like hydrogen, most probably hydrogen, right? So there is a special term, if you can see over here, this says these hybridized orbitals are sp3. So what does it mean by sp3 hybridized? So sp3 is normally telling you which orbital normally took part to form these hybridized orbital. So how you got this hybridized orbital? You mixed 1s orbital which is this, the s orbital, and then you mix how many p orbital? 3 of them. So you use 3p orbital, 1, 2, 3. So this sp3 hybridized orbital normally tells which of the orbital normally took part to form this hybridized orbital. So what's the purpose of this hybridized orbital? To make a bond, to make 4 different bonds for carbons, right? So so how does this hybridized orbital looks like? It looks like a dumbbell, something like this. So this is sp3 hybridized orbital. And how many hybridized orbital you formed by mixing all s and p orbital? 4 of them, if you remember. So you're gonna form 4 So if this is carbon at the center, so this is one of the sp3 hybridized orbital, this is second sp3 hybridized orbital, this is third, this is fourth, and each of them has one electron. If you remember from the previous slide, so each orbital had how many? One electron, right? So these are one electron. So so now they are single pair. How many bonds this carbon can form? They can form 4, because each unpaired electron can take one extra electron to get pair. So this comes from hydrogen. So let's say this circle normally show you the hydrogen. This is hydrogen, and the hydrogen has how many electron? 1. So they share with one of the sp3 hybridized orbital. So now this way carbon can form 4 bonds through sp3 hybridized orbital. So I can make the same structure like this again. So this is carbon, this is bond, this is bond, this is bond, this is bond, and this is hydrogen, right? And if we talk about these bonds, this is sp3 hybridized bonds. Right, they form by sp3. So so I can say this carbon is sp3 carbon, right? Because this carbon using sp3 hybridized orbital to make all these 4 bonds, right? Get to the next slide, which is again bonding characteristics. So this is the same explanation that I already told you. So if any compound or any atom has 4 bonds, let's say in this case carbon has 4 bonds, they always form a tetrahedral shape. So what is tetrahedral shape? This is a tetrahedral shape, and where you have the bond angle. The bond angle is between 2 consecutive bonds. So this is one bond, this is second bond. So what is the angle between 2 consecutive bonds? Is 109. So you have to remember this. In sp3 hybridized orbital or sp3 carbon, we normally has the shape is tetrahedral and bond angle is 109.5 degree. So you have to remember this thing, right? And this is the planar representation, how you normally draw on the 2-dimensional space, carbon 4 hydrogen. Okay, so now let's take an example. So I already told you carbon can form 4 bonds, and then let's take an example. This is carbon 1, this is carbon 2, right? So carbon can form a bond with another carbon, right? So let's take an example over here. So as I already told you that carbon form 4 hybridized orbital. So this is one of the hybridized orbital, this is second, this is third, this is fourth, right? Similarly, second carbon also form 4 hybridized orbital. This is 1, this is 2, this is 3, this is 4, and each hybridized orbital has one single electron. If you remember, this is one single electron. Similarly, second carbon also has the same. This is electrons, right? Electrons. So and then one electron is here. I forgot to put. So if you can see, the bond between carbon and carbon is shared by equally one electron from each side, or by overlapping of, I can say, by overlapping of hybridized orbital. Right, so so those bonds that form by overlapping of hybridized orbital, we call those bond as sigma bond, and we normally have this sigma bond. Right, but now there's a problem that one of the sp3 hybridized orbital from both the carbon is already shared and they already have a pair of electron, but what about the other three hybridized orbital? So they're gonna share it with an hydrogen atom, because hydrogen atom has one electron, they're gonna share with carbon. This is hydrogen, one electron comes from hydrogen, and this is hydrogen. So so this is sigma, so I can draw the exactly the same structure, something like this. Right, and we call this bond as sigma bond. This is a notation how we normally draw sigma bond. Right. Okay, so we already talk about sigma bond. So now let's get to the, so let's say if I ask you this question, what is the hybridization of this carbon? If I ask you, this carbon has a hybridization of what? Hybridization, whether it's sp3 or something else. So how you gonna figure it out? So you have to see this bond is not formed by hybridized orbital, right? This bond is also formed by hybridized orbital, as you can see over here. This bond also formed by hybridized orbital, right? And this is also formed by hybridized orbital. So if you have 4 single bond or 4 hybridized orbital making a bond, that means this carbon has sp3 hybridized state. You can say this carbon is sp3, right? And what's the shape of this carbon or this compound? Tetrahedral. We just remembered from the last slide, right? If any carbon has sp3 hybridization, it has the shape of tetrahedral. And what's the angle? 109.5 bond angle, right? So let me give you one more example on this. Let's say if you have this carbon, this is hydrogen, and we know that each carbon already have 4 bonds. This is carbon number 1, carbon number 2, 3. So carbon number 1 already have 4 bonds. 1, 2, 3, 4. Similarly, carbon number 2 already have 4 bonds. 1, again 2, 3, 4. Carbon number 3 already have 4. 1, 2, 3, and then 4, one more. So each carbon already have 4 bonds. So this structure is right. So if I ask you, What's the hybridization state? For all three carbon atom, that is carbon 1, carbon 2 and carbon 3. So how you gonna figure it out what's the hybridization state for each carbon? So what you need to do, you have to look how many single bond that you have. So this bond is formed by hybridized orbital. If you remember, carbon has 4 hybridized orbital, right? So if you have 4, 1, 2, 3, 4, that means it comes from sp3, because this is 1 and 3 comes from here. So 1 plus 3, 4. So that's why you have 4. So you have to just see all the single bond, how many single bond carbon is making, right? And then we're gonna figure it out some other compound and then see how we can figure out the hybridization state once we go forward into the lectures. Okay, so so we already talked about the hybridization. Let me give you one more example. Is it possible for carbon to make a two bond between a carbon? Right now we have just one, right, single bond, but is it possible for carbon to make a 2 bond or 3 bond between carbon? So let's take an example. So this is carbon 1, this is carbon 2. You have 1, how many electrons? 4, 1, 2. You have 3, you have 4. Same thing for the other 1, 2, 3, 4. They're gonna share the electron, so this is 1 bond. And let's imagine you have just 4 hydrogen. Imagine you have 4 hydrogen. That means 1, and each of the hydrogen is gonna form a bond with carbon. So this is bond, this is bond, this is bond, this is bond. So now you have 4 hydrogen bonded with 2 carbon. Now the problem is, right now carbon has how many bond? 3 bond. 1, 2, 3. On the second carbon again 1, 2, 3. But like I told you that carbon has to have 4 bonds. So what's gonna happen? So the carbon says to each other, okay, let's share these electrons. So now they're gonna share the electrons. They're gonna come over here and they're gonna make a bond, and then this electron will remove from here. So that means carbon can form double bond. Similarly, carbon can also form a triple bond. Why? Because out of the 4, so let's take one more example. Again, carbon, you have 1 electron shared, and you have how many electron? 3 on it. 1, 2, 3. And then again, let's imagine right now you have just 2 hydrogen. How you gonna put hydrogen? 1 hydrogen over here, another hydrogen, let's assume, is here. So what's gonna happen? They're gonna make bond. So right now how many bonds each carbon has? 1, 2, 1, 2. So is it not possible, right? Carbon has to have 4 bonds. So what they're gonna say? They say, okay, we don't have enough hydrogen to make a bond for, let's share other 2 electron from each other and form a triple bond. So they're gonna come over here, this electron is gonna come over here, this one come over here, and this one come over here, and then they're gonna make triple bond. They're gonna go remove from here, and now they are here, so they can make 3. So this is we call as double bond, and then this 3 bond we call as triple bond, and we're gonna learn about this how carbon make double bond and triple bond. But for this particular lecture, we're gonna focusing on just on the single bond. Single bond, right? And now let's talk about the organic compound. Like I already told you, organic compound is a compound made from carbon and hydrogen atom. But sometimes this organic compound also contains some non-metals such as oxygen, sulfur, nitrogen, phosphorus and halogens. And where we can find this organic compound? So we normally find organic compound in mainly in some common product that we usually use in everyday life, such as gasoline, medicine, shampoos, plastic and perfume. So we are using organic compound in our daily life. And how we gonna make a formula for the compound? We normally write carbon first, then hydrogen, and then some other element, right? So this is the way we normally write the organic compound formula, right? Carbon 1, then second, and then any other element like CHO, CH, and right, something like the other element. So you need to know how we normally write the organic compounds. So now let's talk about the hydrocarbons. So hydrocarbons are organic compounds that contain only carbon and hydrogen. So as the name is already saying, hydrogen, and carbon means carbon. So hydrocarbons are those organic compounds that contain only carbon and hydrogen, or they are made up of carbon and hydrogen. So there are four different, we can classify hydrocarbons into four different parts. We can say saturated and unsaturated hydrocarbons. So I can write over here hydrocarbons. I can divide into saturated and unsaturated. So what are saturated hydrocarbons? Saturated means hydrocarbons or carbon compound that contain only single bonds. Unsaturated hydrocarbons are those hydrocarbons or carbon containing compound that contain double bond, or triple bond. They are unsaturated, right? So now let's go to this picture that is shown on the PowerPoint. So hydrocarbon can be saturated and unsaturated, and then the example of saturated hydrocarbon is alkanes. Like I already told you, those compound that contain only single bond. If you can see, they are all single bond, right? So this is just one example of saturated alkanes, saturated hydrocarbons. Where is unsaturated? There are multiple examples. One of them is alkene, alkyne, and aromatic hydrocarbons. So what is alkene? That contain a double bond. Alkyne that contain at least one triple bond. And aromatic compound we're gonna talk about later in the class or in the video. Okay, so from now on, if I say or tells or say alkene, so you should be knowing that I'm talking about carbon containing compound that only contains single bond. If I say alkene, the compound should contain at least one double bond in the compound. Alkyne has a triple bond, right? So keep this in mind. This will be very helpful while we try to name the hydrocarbons. So now let's talk about and start with saturated hydrocarbons called alkanes. So in this video we're gonna mainly talk about alkanes. What is alkane? What are the properties? And how we name these hydrocarbons. So what is alkane? And like I already told you, this is saturated hydrocarbon, and this compound contain only single bonds, right? And what's the general representation of this formula? It's CnH2n. So I'm going to talk about what this formula tells you once we goes to the next slide. But make sure you remember this CnH2n, where n is number of carbons, right? So if n, it normally tells you about how many carbons atom you have in the compound, right? And there are a couple of examples. Methane, CH4 is the simplest alkane which is found in natural gas. Ethane we normally use in natural gas. Propane we use in homes, heating homes and cooking, as well as an industrial fuel. So now let's try to learn how we normally name alkanes. Okay. So depending on how many carbons you have in a compound or saturated compound, we name the compound differently. If you have one carbon, we call as meth. If you have two carbon, we call as eth. If we have three, we call as prop. If we have four, but. 5 is pent, 6 is hex, 7 is hept, 8 is oct, 9 is non, and 10 is dec, DEC, right? The first three letter. So don't worry about the last three letter AN, ANE, AN, AN, AN. I'm gonna tell you about why is methane, why is the name is ethane, right? So if you look over here, if you have one carbon, if you have two carbon, if this compound has 3, 4, so by looking at how many carbon atom you have, you can easily name it, right? You have 9 and 10. Right? So now let's go to the next slide. How we normally represent any alkane or any saturated hydrocarbons. So alkane molecule can be represented in several ways as a molecular formula. So what is molecular formula? That tells you about how many carbon hydrogen atom you have. Hydrogen or any other atom you have. Atoms present in compound. So it tells you this is the simplest formula that tells you how many carbon, hydrogen or any atom that you have in that particular compound. For example, if I say C2H6, this is the molecular formula. So by looking at this formula, I can easily say this compound has 2 carbon and 6 hydrogen. But we don't know the structural formula, how does it look like in structure, but we know this compound has 2 and 6 carbon and hydrogen atom. Second one is expanded structural formula. What is expanded? So if you have C2H6, can I expand it? Can I just open it completely? Yes. So I can write this. We have 2 carbon, right? Make a bond between carbon. Always make a bond between the carbon. You cannot emit or leave any carbon without a bond, right? First always make a bond between carbon and carbon. How many carbon atom that you already have in the compound. Now you have 6 hydrogen over here, so you have to make 6 hydrogen somehow on these 2 carbon, and we already know each carbon can form 4 bond. So 1 bond is already formed, then you have 1 2 3 no 4 1 2 3, now you have 4. So now each carbon can get 3 hydrogen. So this is we call as expanded structural formula. That means you are expanding it from this molecular formula. You just expand it. So expanded means you can literally say that you have to show each and every bond clearly. Now we have condensed structure formula. What is condensed means you have to still show the bond, but you have to just show the bond between only carbon and carbon. So I can write the expanded structure formula into a condensed structure formula, something like this. So I can write CH on this carbon. How many hydrogen is attached? 3. 1 2 3 3. Then you have this bond, then you have this carbon. How many hydrogen on this carbon? 3. So CH3 bond CH3. So you usually don't show a bond between carbon and hydrogen. You just show between carbon and carbon, which is this bond. This is a condensed structural formula, right? Then we have line angle formula. What is line angle? As the name is saying, you have something like this. So this is a line and is bending, again bending, so you are making an angle between two consecutive lines, right? This is an angle and this is line. So that's why we call as line angle formula. So what's special about this line angle formula? If we see this line angle formula, each starting point and each turning point where the line is turning, this represent a carbon, right? So how many carbon you have in this line angle formula? 1 2 3 4 5 6. You have 6 carbon in total, right? Let's say, for example, one more example. You have this line angle formula. How many carbon you have in this? Can we say I have, this is one starting point, this is turning point, this is an ending point. So we have 3 carbons, right? And in line angle formula we usually don't show a hydrogen. Can you see the hydrogen atom? If I already drawn it on each carbon? No, I didn't draw any hydrogen in there. Why? Because we already know how many hydrogen is already attached to the carbon. For example, let's take this carbon. How many hydrogen you think is attached to this carbon over here? 1 2 3 4. How many? So let's see. So it has to be 3, right? Because this carbon already have one bond to the second carbon, right? So how many more bond this carbon need? 3. Hydrogen, 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 right? But we usually don't show hydrogen in the line angle formula. So remember this thing. If you're not showing hydrogen, the hydrogen is still there, but we are not showing it, right? So that's the difference between line angle and all other formula, condensed and expanded, where you usually show the hydrogen, right? So keeping this in mind, this is important too. Okay, so this is again a different molecule, C4H10. This is your molecular formula. Right, this formula tells you we have 4 carbon and 10 hydrogen. This is expanded. You have 4, 1 2 3 4, and each carbon has 4 bond. This is condensed. You have this carbon. How many hydrogen? 1 2 3. So this is 3. This is second. This carbon has how many bond? Just 2 hydrogen. That's why you have 2 in here. Third one, you have again only 2 hydrogen. That's why you have 2 hydrogen. And the last one has 3. 1 2 3. So that's why you have 3, right? So and then this is a line angle formula. 1 2 3 4, C4H10, right? So again it's same, 1 2 3 4, right? And the important thing over here, you can make a condensed structural formula as long as you're not breaking any bond. If you can see from, let's start from this end. If you see this carbon is attached to this, you are making a straight line, right? The bond is continuous. You can make the same condensed structure formula something like this. This is also right. Why? Because you are having a continuous line without breaking it. Same thing over here. As long as your line is not breaking and you are covering all carbon that is present in the compound, that means those are same compound, right? So that's why you have different condensed structural formula in here. So now let's try to solve a couple of problems on this concept. So let's try to solve this formula. Given the following expanded structural formula, provide. So this is the expanded structure formula. You have to write the molecular formula, then you have to write the condensed structure formula, and then you have to write the compound name. We haven't learned how to name right now, but once we will learn, you can easily name this compound too. So let's start with the molecular formula. How many carbon you have? 1, 2, 3, 4, 5. So we know we have 5 carbon. How many hydrogen we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have 12. So C5H12. How we can write the condensed structure formula? Can I write this? On the first carbon, how many hydrogen we have? 1, 2, 3. CH3. Then you have on the second you have 2 hydrogen, CH2. On the third you have again 2, CH2. Third one again 1, 2, CH2. And the last one we have 3, 1, 2, 3. So this is the condensed structural formula where you can see carbon and hydrogen and the bond between only carbon and carbon, right? So we're gonna learn how to name this compound, but I'm gonna write right now, but you can see it later on. So the 1, 2, 3, 4, 5, the name is pentane, but you're gonna learn how we're gonna name all this compound, alkane compound. Okay. So now next slide. So this is the solution that is already given, right? So you can see the solution already over here, but I already solved for you in the previous slide. So this is second learning check. Write the condensed structural formula for ethane. So we don't know what is ethane is, but we already know what is eth mean. How many carbon we have in, if I say eth? Can I say 2? If I say hept, how many carbon we have? 7. So if we already know how many carbon we have in each of them, we can make a condensed structure formula. Yes. So let's make for ethane. So this is 2, 1, 2, and you have to make 4 bond. 1, 2, 3, 1, 2, 3. Hydrogen, 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 hydrogen. So that's your ethane, right? For heptane, you can say you have 7 carbon. 1, 2, 3, 4, 5, 6, 7. And like I told you, you have to make a bond between each and every carbon, right? So so how many bond you need? 1, 2, 3. Hydrogen, hydrogen, hydrogen. How many bonds hydrogen you need to be on this carbon? Second one, just 2. Why? Because 2 bond is already there, so 4 bonds. Same thing on this. So this is your heptane, but this is your expanded structure, right? This is your expanded structure. But how are we gonna write the condensed structure? Can I write the condensed structure like this? For this one as CH3, you have carbon and 3 hydrogen, then bond, then second carbon 3, CH3. So this is your condensed formula. Same thing for over here. On the first one we have 3, second one we have 2, third one 2, then again 2, then last one as 3. So this is your condensed formula again, right? And this is your expanded one. Okay, so let me give you one more example on this. Can we make a condensed structure formula for pentane? We know pent mean 5 carbon, and we can make expanded structure 1, 2, 3, 4, 5, and then put hydrogen. So this is your expanded structure, right? But we have to make a condensed structure. How are we gonna make? CH3 bond CH3 bond, CH2 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 and CH3. So 1, 2, 3, 4, 5 carbon. Right, so this is your condensed form. If I ask you write the molecular formula, so what's the molecular formula for this compound? So molecular formula gives you how many carbon and hydrogen you have. So how many carbon you have? You have 5 carbon. How many hydrogen? 3, 4, 5, 6, 7, 8, 9, 12. So this is your molecular formula for pentane. So this is a solution from the previous question that I already solved for you. You can see it over here again, but I'm gonna skip this part. So now let's try to so now we're gonna talk about a term called isomerism. What is meant by isomerism? So isomer is a property of a compound which has two or more compounds. Is the property of two or more compound that has same molecular formula. This is important, but different arrangement of atom. Means two or more compound can have the same number of carbon, hydrogen or any other atom, same molecular formula, but when you draw the expanded structure form, they might look different. So let's take an example. One of the type of isomerism is called structural isomerism. Means this is difference between the structure while you're making a structure from the same molecular formula. So let's understand what does it mean. So this is C2H6, we call as molecular formula that we learn, right? This is a molecular formula, but from the same molecular formula I can make two different structure. This is structure 1, this is structure 2. So if you can see, each of them has same number of carbon, 1, 2, 2 carbon, 6 hydrogen and 1 oxygen. Same thing, 2 carbon, 6 hydrogen and 1 oxygen, right? They have same molecular formula, but when we drew the structure, they looks different. Why? Because in the first structure, oxygen is present between carbon and hydrogen, but where in the second structure, this oxygen comes between 2 carbon. So they have different structure or different arrangement of atom, you can say arrangement of atoms, right? So you just rearrange oxygen and atom, right? So this is called isomerism, and specifically structural isomer, because structurally they looks different even though they have same molecular formula, right? So make sure you remember this thing, what is isomer and what is a structural isomer. So now let's take an example and try to solve this problem. Draw 3 possible structural isomer of pentane C5H12. This is molecular formula. And you have to make a structural isomer, means you have to draw 3 structure that are different from each other, or there has to be different connectivity of atom. Let's try the first one. Can I draw the first one like this? 2 CS2 CS3. Second one CS3 CH CS3 CS2 CS3. Third CS3 C CS3 CS3 CS3. So if you can see there, for each different structure you have different connectivity of atom. So let's try this. This is number 1 carbon, second carbon, third, fourth, fifth. 1 2 3 4 5. 1 2 3 4 5. If you can see in the first structure, if you start from the first carbon and go all the way to the 5th carbon, all the bonds are in continuous length, right, or continuous bond, right? You don't have to break. If you start from 1 to 5th, it is a continuous bond. But if you go to the second structure, if I start from the 1, go straight continuous, but we cannot reach the 5th carbon over here. Continue, we have to break, stop here and then come over here, because there is no bond between 4 and 5, right? So what does it mean? So one of the carbon from the first structure, you took it, broke the bond and then switch it on the second carbon. So that means you are making a new compound, means you are rearrange the carbon atom, right? You took it from here and put it over here. In the third structure, what you did, again, if you start from the first, if you go all the way to the last carbon, you are just going from 1 to 3, right? You don't have any bond between 3 and 4 and 4 and 5. That means the connectivity is now different than 1 and 2, right? So what you did, you took the 4th also and put it on the second. So you are breaking the bond and then just putting the molecule in a different carbon atom than the previous one, right? So this is how all these 3 are structural isomer of each other, even though they have same molecular formula C5H12. You have 5 carbon and 12 hydrogen, but in structurally they are different, right? Okay. So now let's get new slide. So this is the solution that I just explained you about, how you make a condensed structure formula, and you can also make a line angle formula, right? So this is 1 2 3 4 5 is all straight line bond, right? But for the second structure, 1 2 3 4 and the 5th is now is present on the second carbon. You just broke this carbon bond and put the 5th carbon on the second, and on the last one, what you did, you broke this bond and put the 4th carbon again on the second. right? 1 2 3. So now you have two carbon attached to the same second carbon, right? So they are structural isomer. They have same molecular formula, but structurally they are different. Okay, so now let's talk about another term called conformation. So what is conformation in organic chemistry or organic compound? So different arrangement of atom in space achieved by rotation about a single bond. What does it mean? So let's let me make one bond compound CH H H. So this is a single bond between carbon and carbon, and this is a property of a single bond that you can rotate one of the carbon atom across this single bond. So single bond has a flexibility. You can rotate other carbon atom that is attached to the carbon atom. So take this example. This is first carbon, this is second carbon. If you fix this carbon and then move the second carbon, rotate it through this axis, single bond axis. So what's going to happen if you rotate this, CH3 is going to come over here, and the H will go over here, and H will replace CH3. If you can see in this structure, you rotated the carbon. But does the connectivity between 1 and 2 change? No, still they are bonding with the same bond. Only the carbon rotated, right? The bond hasn't been broken down, doesn't change. That's why both of them is same structure. Right? So they are not different structure, because if you rotate one more time, CS3 will come over here. If you rotate one more time, CS3 will again come on the top, right? So if the connectivity between the carbon is same, that means they are not isomer, they are conformer. So remember this term, conformer, right? So let's take one example so that you can better understand what is meant by conformer. Like I already told you, the bonding between the carbon atom should not be changed in conformation. They have the same connectivity. So let's, which of the following pair represent a structural isomer and which one is just simply the same compound? Means they conformers, if they are conformers. So you have to pick whether these two compounds are structural isomer or they are just simply the same compound or conformers. So how you gonna figure it out? So let's take this example, 1 2 3 4 5. If you start from 1, you can see there is a continuous connectivity, right? You don't have to break any bond. From 1 to 5th you are connecting each and every carbon atom, right? Let's take again 1 2 3 4 5. You have 5 carbon again in this one. So if you start with 1, if you go all the way through the bonds, again you are touching from 1 to 5th without any breaking in the bond between the carbons. So it's a continuous connectivity. Even though the structure looks different, but they are not, because the bonds are continuous from 1 to 5, right? But they are conformer. Why? Because if I just move this bond and hold this carbon and move this compound over here downward, you're gonna make this CS3, right? So these two are conformers. Now let's talk about the bottom two structure. So let's start 1 2 3 4 5. So if I go from 1, go all the way 2 3 continuous, but I can't reach 5, but I can reach 1 to 4 continuously, right? So now let's start from here, 1 2 3 4, 5. So if I go from 1, go all the way to 3, but in this structure we cannot touch 4th because we don't have a bond. So that means this bond has to be broken and then put it somewhere in here, right? So in this case, bond is being broken even though you have the same number of carbon, but the structure is different because the bond is broken and the connectivity is now different. It's not continuous than the previous one. So they are structural isomers. Right. So you have to make sure you know the difference between conformers. In conformers, you won't have any discontinuity between the bond from the first to the last carbon. But in a structural isomer, you have to have some bond being broken and you don't have any continuity that you had in the previous compound. Right. So that means they are structural isomers. Right. Okay. So what's the molecular formula for these two compounds? Can I write 1, 2, 3, 4, 5, C5? How many hydrogen? 3, 4, 7, 9, 12. So molecular formula is same for both of them, but the structure are different. Over here, molecular formula is again same, C5H12. You have 5 carbon, but the structure is same. That's why they are not a structural isomer, they are just conformers. So you make sure you know the difference between conformers and. So till now we learn about what is isomerism, what is structural isomer, what are conformers. Now let's try to learn how to name any alkanes, how to name it. So so we name any hydrocarbon using an IUPAC name, which is International Unit of Pure and Applied Chemistry system. So this is a system normally used by all over the world by the scientists to name any organic compound. So there are certain set of rules that you need to follow to name any organic compound. And if we're talking about alkanes specifically, then we're gonna see the ending of any compound, naming of compound should be ending with ANE. Right. So let's try to solve some example on this, how to name and learn some rules of the IUPAC system. So the step 1, rule 1 is identify and name the longest carbon chain. So you have to figure it out what's the longest carbon chain in the compound given. So let's take an example over here. So you have 1, 2, 3, 4, 5. Right. You have 6 carbon over here. But what it says is you have to pick the longest carbon chain, means continuous carbon chain, and you make sure you always have to start from the corner of the organic compound, means you have to start counting from the free carbon, right? So that means this carbon is free, this is the last carbon because over here you don't have any carbon attached. This carbon is free because it doesn't have any more bond on it. This carbon is free because it doesn't have any more bond after this. So you can start the counting. So you have to pick the longest chain. If I start from here, 1, 2, 3, 4, 5, and this is continuous, we are not breaking any bond, but we cannot go from 5 to 6 because there is no bond in there. So you have to pick the longest chain. So instead of this chain, if I would have picked the other one, let's try a different one. If I would have started from here, 1, 2, if I would have gone 3 over here, does it make a longest chain? No, this chain has only 3 carbon in there, which is smaller than the previous chain that we had 5 carbon in there. So this is not the longest chain, so we are not going to take this chain as our main chain, right? So this is your longest chain, continuous chain, and this longest continuous chain we call as parent chain. So remember this thing. Okay, so what's the second? Number the longest chain to give the lowest number to any carbon which is a group attached. So if we already figured out which is our parent chain, this carbon is not part of the parent chain, right? So that carbon that is hanging from the parent chain, we call that carbon as substituent. So remember this thing, those carbon or carbon atom that is not part of the parent chain, we call that as substituent, right? Okay. Now the third one is locate and name the attached alkyl group. So this substituent we also call as alkyl group. So make sure you know what is alkyl group is a substituent that is attached. So now you have to locate and name the attached alkyl group. So how many carbon, how to name this substituent? So you have to look for how many carbon you have. So how many carbon you have in this substituent? Just one. And if you have just one carbon, if you remember from the table, if you have one carbon, the name is meth, right? And then you have to just write YL at the end, because substituent ending should be with YL, so the name will be methyl. So remember this thing. So this substituent is methyl. Meth because you have one carbon, YL because this is a substituent, so that's why it's methyl. So now you have to see from which end you have to start counting. So now they have two possibilities. Start counting from here 1 2 3 4 5, or I can start counting the other way around, 1 2 3 4 5. So which counting is correct? So make sure you have to count from that end, from the parent chain that gives the lowest number to the substituent. So in this, if I count from here, the substituent is attached on the second carbon. But if I would have counted from the top, the substituent is attached on the fourth carbon. So that means you have to start counting from this end, from the right hand side end, because this, by counting from the right hand side end, you are giving number 2 to that carbon that has the substituent attached, right? So this is the another rule. And the last one is you have to just name the molecule. So how we name it? So let me erase everything and just start naming it. So this is your parent chain. So this compound is your substituent, this is methyl. And how to name the parent chain? You have to count 1 2 3 4. So 5. If you have 5 carbon, what's the name? Pent. 5 carbon is pent, but because this is an alkane, the ending word should be ane. That's why it's called pentane, right? If you have 6 carbon alkane, that means hexane. If you have 7 carbon, heptane, because 7 is hept, and because this is alkane, your ending word has to be ane, heptane, right? So how we normally name the alkane or any organic compound? So you have to follow this sequence. You have to write first substituent, then you have to write parent chain, locate number. So what is locate number? Means the number of the substituent. So in this case, second carbon has the substituent, so that's why you have 2, and then between the number and alphabet you have to write a hyphen, so that means 2 hyphen, then you have to write the substituent name. What is substituent name? Methyl. And then you have to write parent chain. What is parent chain? Pentane. So the name of this compound is, let's go to the step 5, rule 5. If you have a multiple branches, means if you have multiple substituent. Branches means substituent. Show the location of each branch with the number. If you have multiple branches with the same time, modify the name with di, tri, tetra. Di means 2, tri means 3, tetra means 4, right? And keep on, and separate the position by commas. List multiple branches alphabetically. So let's try to solve one problem on this and then try to understand this rule number 5. So let's take an example. So if we have CS3, CS2, 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 then let's make CS3 over here and remove one of the CH over here, and then remove this bond over here. So now let's try to name this compound from the rules that we just learned. So first rule says you have to figure it out what your parent chain is, the longest chain without any discontinuity. You have to go continuous. So you have to start counting from the free end. This is your free end. You can start count from here. You can start counting from here because after this carbon there is no bond. There is no more carbon atom. You can start counting from this. You can start counting from this carbon. So now let's start counting. If you start from here, 1, 2, 3. If you go up, this is 4. So this cannot be our main chain because this is not long enough, because we already seeing we have long. If we would have gone straight, we could have gotten like more number of carbon in the parent chain, right? So we cannot go up. So let's go straight. 3, 4, 5, 6, 7. And then before we go, this is also CS3. Okay, so if I go straight, this is 8. So maximum number we can get 8. But if instead of going straight, if I would have gone top, this is 8. So it doesn't matter whether you go straight or up, doesn't matter, because the maximum number of carbon that you are getting is 8. So whenever you have a choice, always pick a straight chain. That will help you to figure it out what's your substituent. So this, so this will be my parent chain, the longest chain. This is my parent chain, right? Parent chain is the longest carbon chain. So we already figured it out. The second thing is, once you figure it out, the parent chain, you have to figure it out what's your substituent or branch. So if you can see over here, this CS3 and this CS3, this is not part of the parent chain. So if this is not the part of the parent chain, they are substituent. right? They are substituent. And then how you name substituent, you have to see how many carbon you have. You have one carbon in there, so this is meth, one carbon, but this is a substituent. If you remember, I told you the substituent end with YL, so this is why this is methyl. This carbon is also a substituent, and this is just one carbon is also methyl, right? So you have two substituent and both of them are methyl group, right? So what's the third rule? So the third one, you have to see from which end you have to start counting. You have two ways to start counting the parent chain. Either you have to start from this end, left hand side, or from the right hand side. Now you have to pick which end you have to start counting. So the rule says you have to start counting from that end that will give you the lowest number to the substituent, right? So let's take this example. If I would have started from this end, the left hand side, 1 2, the first substituent is occurring on which carbon? Third. And then the second substituent is occurring on 7th carbon, right? But if I would have started from the right hand side, from this side, this will be my carbon number 1, this is carbon number 2, 3, 4, 5, 6, 7, 8. So let's imagine if I would have started from here, the first substituent is occurring on which carbon? Again second, it's occurring on second. The second substituent is this one over here, is occurring on 6th. So which end we have to start counting? So you have to start counting from that end that give you the lowest number of the substituent. So the lowest number, the first point of difference is 2. So we have to start counting from the right hand side. This is the correct way of counting, right? So make sure you have to pick from which end you are getting the lowest number to the substituent. That's it, very important. So so now let's erase everything. So let me give you one more. It's the same example that I gave you. CS3, CS2, 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 1 2 3 4 5 6 7 8, and then so you would have one on this and one on this, and remove this one. So we have to start counting from this end. 1 2 3 4 5 6 7 and 8. So what's the rule says? You have to write the location of the substituent first. So first substituent is present on the second, you write 2 hyphen which substituent you have on here? Methyl. This is your parent chain, right? So it's 2 methyl. Then again you have a hyphen, and the second substituent is present on which location? 6 methyl, because on the 6th carbon you have methyl group again. Then you have 8 carbon in the parent chain. What's parent chain? 8 is octane. Oct is 8, and because this is alkane, ending would be ane, right? This is alkane ending, so the name will be 2-methyl 6-methyl octane. So this is one way of writing. But if you have the same substituent methyl, in this case methyl, you don't have to write 2 times 2-methyl 6-methyl. What you can do, you can just specify the location. You have the substituent on the 2nd carbon, comma, you have the substituent on the 6th carbon, and which substituent, same substituent you have, methyl. So I can write methyl, but you have 2 methyl, you have to use di, that is 2,6 dimethyl octane. That's your parent chain. So we usually use this form of naming rather than the top one, because you have to just specify the location of the same substituent. Just write how many times the same substituent appear in the parent chain. 2 times is di, 3 times is tri, and then the parent chain. Right? So this is the name of this. Let me give you one more example. But this time in a line angle formula. So what's the name of this hydrocarbons? Alkane. So this is in the form of line angle formula, right? So each free end, this is carbon, this is carbon, this is carbon, carbon ending, corner is carbon, right? So this, you have to apply the same rule. Pick the longest chain. So you can start from here, 1, 2, 3. You can go up and write 4, but we can already see that we have more number of carbon if you would have gone straight, so we don't have to go up. So this is 4, this is 5, this is 6, this is 7. So we cannot have more than 7. So let's try the other way around. Let's start from this carbon. 1, 2. Now I have a choice. Either I can go left hand side or right hand side. So let's go to the left hand side. 2, 3, 4. So this is not possible because we already got 7 carbon in the previous parent chain. So that means we cannot start from this carbon and then go on the left hand side. So this cannot be our parent chain. Now we have a choice. Go to the right. 1, 2, 3, 4, 5, 6. If I'm going from to the right, we are getting just 6 carbon, which is still less than the 7 carbon that we've already got from the first parent chain. So this will tell us that the main parent chain will be the first one that we just did. So just remove each other numbers. So our parent chain will be this one. This is our parent chain, right? And then what's this? This is our substituent, right? And then how many carbon you have on this? 1 carbon. If you have 1 carbon, that is meth, because this is substituent, this is methyl. So this is your methyl group as a substituent. Now you have in the second other rule, now you have to decide which end you have to start counting. Either you have to go start counting the parent chain from left to right or right to left. So you have to pick carefully, because the rule says you have to start from that end of the parent chain that will give you the lowest number to the carbon that has the substituent attached. So from the left hand side we have to start counting 1, 2, 3, 4, 5, 6, 7. So how we name this organic compound? So we have to write the location first, which is 3 hyphen, then write the substituent name, which is methyl, and then the parent name. What's the parent name? We have 7 carbon altogether. 7 is hept, H-E-P-T, and this is alkane, heptane. So the name will be 3-methyl heptane. Okay, so we already talked about alkane with a substituent. Let's take an example over here. On the right hand side, what's the name of this molecule of this alkane? So we have 1, 2, 3, 4. 4 is but. So this is butane because this is alkane. Ending word should be ane, butane. What's the name of this molecule? The second one that we have over here. So we have how many free carbon? This carbon is free because it doesn't have any carbon on the top. It doesn't have any carbon on the left hand side, doesn't have any carbon on the right hand side. So they are free carbon, they are on the corners. So if we start counting from here, 1, 2, 3. So we can get 3 carbon at the parent chain. But if I would have started from the top, 1, 2, now we have to decide either go left or right. If I would go left, 3, or if I would go to the right, 3. So it doesn't make a difference, still we are getting 3. So it doesn't matter which way we have to go, we are always getting a maximum number of 3 carbon in our parent chain. And I already told you, if we have a choice, then always pick the straight chain. So we're gonna pick the straight chain, which is this one. And now we have to write the name, write the location of the substituent. Substituent is this, which is methyl, 1 carbon, so it's 2 methyl, and we have 3 carbon in the parent chain. 3 carbon is prop, but this is ane, this is propane, this is 2 methyl propane, the name of this molecule. So till now we just learned about what are substituent, what is alkyl group. But instead of the carbon as a substituent, we sometimes have some halogens. Like chlorine, iodine, fluorine. Chlorine, bromine, iodine, fluorine as our substituent that we call as halo substituent. We usually write substituent for halogen as, if it's a fluorine, then fluoro. If this is chlorine, then chloro. If it's bromine, bromo. And if it is iodine, then as iodo. So if you find any of these substituents attached to your parent chain, you have to just write fluoro, chloro, bromo, or iodo, depending on which halogen is attached to your parent chain. So this is couple of example of the substituent we already talked about. If you have 1 carbon as a substituent, methyl, 3 carbon propyl, 4 carbon butyl, right, and then fluoro, chloro. So depending on how many carbon you have on the substituent, you just write the required name. So let's try to solve one problem on the ionic nomenclature of this alkane. So how many carbon we have in the parent chain? Let's start counting. If this is a free carbon, this is free carbon, you don't have any carbon on the right hand side. Over here you don't have any carbon on the left hand side, free carbon. This is your carbon, free carbon. So you can start from this end too. So let's start from the left hand side first. 1, 2, 3. Now I have a choice. I can keep going straight and then write 4, 5, or I can go bottom on the downside, 4. So is it not possible to go down, because the maximum number of carbon that you're getting is 4. So we have to pick the straight line because we are getting 5 carbon, the maximum number of carbon chain without breaking a bond, the continuous chain. So this is our parent chain. And then if this is our parent chain, this has to be our substituent, and this is one carbon, so this is methyl group. So that, and then we have to pick which end we have to start counting. So in this particular case it doesn't matter, because if I would have counted the opposite way from right to left, 1 2 3 4 5, the location of the substituent is still occurring on the third carbon. So it doesn't matter whether I go from left to right or right to left. In this particular example it doesn't matter, because this substituent is always occurring on the third carbon. So it's up to you. So I'm starting from left to right from this side, and then I'm gonna write the location of the substituent, then methyl, and then but before I write this name, we also have one halogens over here. If you can see, this is chloro, this is chlorine, so we have to write chloro, and then this is methyl. Now there is a problem. Now you have to pick, because you have two substituent attached on the parent chain. Now you don't have any option. You have to pick the right carbon from where you have to start counting. You don't have a choice to start either end, because of this chlorine attached on the second carbon. So if I start from left to right, the first substituent is occurring on the second carbon, and the second substituent is occurring on the third carbon, right? If I go from right to left, our first substituent is occurring on the third carbon, and the second substituent chloro is occurring on the fourth carbon. So which one is a winner? Which end is a winner? The left to right end is a winner. Why? Because this is the lowest location of the substituent if you're going from left to right. So we have to pick or start counting the chain from left to right. So I can say, so we have chloro and methyl as a substituent. So if you have multiple substituents, so let me write over here, if you have multiple substituent, then you have to name the substituent alphabetically. You have to see which one comes first in the alphabet. So chloro and methyl. So chloro, C comes first in the alphabet. So we have to write 2-chloro hyphen on the third carbon we have methyl, and then you have to write the parent chain. Parent chain has 5 carbons. 5 is pent, and then ANA, because this is alkane, so pentane. So the name for this compound is 2-chloro-3-methyl pentane. Okay. So this is a solution that is already given for your. This is everything is explained that I already explained to you how to name the compound, but you can read it from this slide too. So let me give you one more example of practice of naming the alkene. So okay, so this is the organic compound that you need to get the name for. So again you have to apply the same rule. Find the parent chain, the longest chain. So how many free end you have? You have this carbon, you have this carbon over here at the end, you have this carbon, and you have this carbon. So you have 4 free end that you can start counting for. So let's start counting from this end, from the left hand side. 1 2. If I go up, then we will have 3 carbon, which is not possible because I can see I can get more than 3. So I'm not going up to 3 over here. So I'm going straight 3. Now I have a choice. I can go keep on writing 4, 5, 6, or I can go down, or I can write 4, 5. So I'm not going to go down. Why? Because I can already get 6 carbon if I go straight. So there is no point of going down. 6 over here. So this cannot be our parent chain. If I start from this carbon over here, so if I start from here 1, 2, 3, and then if I go down again 4, 5, which is not possible because we can easily get more than 5. If I go straight, then 4, 5, and 6. So still we are getting 6 if we start from the top carbon or the bottom carbon, right? So we have a choice. Either we can go from straight or from the bottom, right? So let's start counting. Let's start the straight one. So let's remove this carbons. So let's start counting. So this is our parent chain with a 6 carbon, and then these are our substituent. This is our substituent. This is our substituent. Right? So this substituent has 2 carbon. This is 1, this is 2. So you have 2 carbon substituent, means 2 carbon is eth, and because this is substituent, this is YL. 1 carbon is meth, and this is methyl. So we already know. So now we have to decide which end we have to start counting, from left to right or right to left. So again apply the same rule. So if I go from left to right, this is my 1, 2, 3. So the first substituent is occurring on the second carbon, and the second substituent is occurring on the third carbon. If I go from right to left, then 1, 2, 3, 4. Our first substituent is occurring on the fourth carbon, so it's not possible because we are already getting the lowest substituent on the second carbon. If I'm going from left to right, so we have to start from left to right and then start writing the name of this compound. So I can write, so we have on the second carbon we have methyl substituent, and on the fourth carbon what we have, ethyl. But we cannot write 2-methyl 4-ethyl, because if you have multiple substituent you have to write the substituent alphabetically. Whichever substituent comes alphabetically first, you have to write that substituent first. So ethyl comes first alphabetically because start with E, then methyl. So our main answer or main name will be 4-ethyl 2-methyl, and then 6 carbon is hexane. Hex is 6-AN. So this is the name of oh, no, it's not 4, it's 3, my bad. It's 3-ethyl because this is 3. So this is also 3. Right? So still if we have 3, no, this is 4. That's right, that's 4. So this is the right answer. So the answer for final answer will be 3-ethyl 2-methyl hexane, because on the third carbon we have methyl. So on this slide, we're going to learn about if the name is given instead of the structure of the organic compound, how we're going to draw the structure. So in this particular problem, we're going to learn if the name of the structure is given, how we're going to draw it. So the question says draw the condensed structural formula and line angle formula for this compound 3-bromo 1-chlorobutane. So whenever you need to draw, I would suggest always start from the end. So first you have to draw the parent chain. What's your parent chain? Butane. Butane is 4-carbon chain. 1, 2, 3, 4-carbon chain. And then on the first carbon you have chloro. So I'm going to write Cl on the first carbon. I'm assuming this is my first, this is second, this is third, this is fourth. And on the third we have bromine, bromo. And then you have to write the required number of hydrogen. How many hydrogen you need? 2 on this, 2 on this, 1 hydrogen on this, and 3 hydrogen on this to make 4 bond to the carbon. So this is the structure of 3-bromo 1-chlorobutane. So this is your condensed structural formula. Now we have to draw the line angle formula. So again, parent chain 1, 2, 3, 4. Right. On the first carbon we have chlorine, on the third carbon we have bromine. So this is your line angle formula. For 3-bromo 1-chlorobutane. So I would suggest whenever you're going to write or draw the structure, always start from the parent chain first. Draw the parent chain first, and then after that draw the substituent. That will really help you to draw the structure. So this is the solution that I already solved for in the previous slide, but you can read and see it from the couple of that normally tells you how we normally draw the organic compound with the name. So everything is explained. Okay, so now let's try to solve or name the following compound that is given for as an example. So let's start from the A. So we have to start counting the longest parent chain. We have to start count from this end, from the right hand side, because I can see the substituent, which is chlorine, is present on the second carbon, the lowest carbon. 4, 5. If I would have started from this end, our substituent will be occurring on fourth carbon, which is not possible because we already got the substituent on the second carbon. That's why we have to start from the right hand side. That's the correct way. So the naming will be, so this is our parent chain. So the naming will be substituent location, then substituent name. This is chlorine, so you have to write chloro, and then the parent name pentane. This is 2-chloropentane. For part B, we again have to specify the longest parent chain. If I start from here 1, 2, I cannot go 3 down because I can see we have more carbon that we can count. Then go straight 3. Now I have a choice to go up, but I can see if I would have gone over here straight, then I can get 5 instead of 4. So this is not the right way going up. So this is our parent chain. The maximum that you can get is 5 carbon. You cannot get more than 5 carbon. If it doesn't matter if you start from any carbon end. The maximum you can get is 5 carbon. And this is your substituent, which is 1 carbon, which is, we can write methyl. This is also your substituent, 1 carbon, which is methyl. Now we have to see which end we have to start counting. We have to start counting from the same end that I already counted, because from this end I'm getting the lowest number of them on the substituent. Right? If we would have started from here, the first substituent will be occurring on the third carbon, which is not possible because we already got the first substituent on the second one if I started from here. So the naming will be 2,3 dimethyl. Then again we have 5, then pentane. So 2,3 tells you the location of the 2 substituent, which is both methyl. That's why I'm writing di over here. So 2,3 dimethyl pentane. and this is the solution that is already given for you guys, so just read it along. It's the same thing that I explained you in the previous slide. So everything is explained, why we are counting, which end we are counting, and then this is the final answer that I already provided to you on the same slide that has the problem, the question is given. So now let's talk about the cycloalkane. Cycloalkane are special alkane that are cyclic in nature, means they normally form a ring type structure, and they have 2 fewer hydrogen compared to the open chain form. So let's take an example. So this was the name of this compound, 1, 2, 3. 3 is this is propane, and the name is saying this is a propane. This is open chain structure of alkane. Whereas cyclopropane, which is a ring type structure, if you can see, it form a closed ring, closed circular ring or cyclic ring, right? And it has 2 fewer hydrogen atom than the open chain form. That means if you have to make a bond between these 2 carbon, what's gonna happen? You have to remove one of the hydrogen from this end and one of the hydrogen from this end, so that it becomes CS2. Because if you wouldn't have taken out the hydrogen, then the carbon would have 5 bond as compared to the 4, which is not possible. So you have to take out one hydrogen. As you can see, now you have 2 hydrogen, means you already taken out one from this, one from this. That's why you have 2 hydrogen less compared to the open chain form of the alkane, right? So how we normally name any cyclo compound or cycloalkane? We usually write cyclo in front of the name of the alkane. So this carbon, this cyclic form of alkane has 3 carbon, 1, 2, 3. So this is propane again, but this is cyclic in nature. That's why we have to write cyclopropane, right? So let's take one more example. If I give you this structure, the square, this is line angle formula. You have 4 carbon, 1, 2, 3, 4, and we know this is cyclic alkane because close from everywhere. So if you have 4 carbon, that means this is butane, but this is cyclic in nature. We have to write cyclo in front, then write butane. So this is cyclobutane, right? Similarly, if I have this structure, how many carbon you have in this cyclic form? We know this is cyclic, ring-like structure, cyclic alkane. So we have 1, 2, 3, 4, 5, 6. So we have 6 carbon. 6 carbon is hexane. But this is cyclic in nature. We have to write cyclohexane. So you have to just specify by writing cyclo in front of the name of the alkane that you are working with, the cyclic alkane. So there are a couple of examples. Like I already told you, this is cyclobutane. You can write in the line angle formula or you can write in the condensed form. It's up to you. But make sure you know both of them, how you differentiate, right? Similarly, this is cyclopentane. You have 5 carbon, 1, 2, 3, 4, 5. So this is cyclopentane, and the cyclohexane I already told you in the previous slide how you name it. So let's try to do some problem on this. Give the epic name of the following compound. So it's simple. This is a straight chain alkene. 1, 2, 3, 4, 5, 6, 7, 8. This is 8 carbon, and this is alkane. This is octane. Now try to name this B part. In B part, we know this is a cyclic compound. So this is cyclic alkane. So it's up to me or up to you whether which carbon you have to use as number 1 carbon. 1, 2, 3, 4, 5, or you would have gone opposite way. 1, 2, 3, 4, 5. So it doesn't matter. So this is pentane, 5 is pentane, but this is cyclo compound, that's why we have to write cyclo in front. So cyclopentane is the name. Okay, so I don't think there wouldn't be any problem on. So the answer is already provided to you. Right, so this is a solution that you can also refer. Now let's try to name the following alkane again so that you can get more practice. So the first one is 1, 2, 3, 4. Let's try to do it. So the 4 is butane. So this is butane. This is cyclic compound. We can just count the number of carbon that you have in cyclic compound. This is 3. I can write cyclopropane because this prop is 3 carbon. And how many carbon you have in this part C? 5, 6, 7, 8 is again, this is octane, oct is 8, and the last one is 1, 2, 3, 4, 5, 6. This is cyclo compound. I can write cyclohexane because this is a cyclic compound, close from everywhere. Right, so the solution is already given, that I already explained to you in the previous slide. Okay, so till now we just learned about naming the simple cycloalkane, but from now on we are going to see if the substituent is also attached to the cycloalkanes, how we are going to name that compound. So let's try to see this example that is given over here. So you have the cycloalkanes, cyclic compound, and you have one of the substituent. So we are taking this cyclic compound or cyclic alkane is our parent chain, and so this carbon chain is you can treat as a substituent, right? So how many carbon you have in there? 1, 2, 2 is eth, so this is ethyl, right? Now you have to start counting the number. So you always start counting the number from the carbon on the cycloalkane that has the substituent. So this has to be your 1. Then it's up to you whether you can go up to bottom 2, 3, 4, 5, 6. But the main thing is that you have to give the priority to the carbon that has the substituent attached. So this is 1. So the name will be methyl. You always have to write the substituent. You can write the location, 1-methyl cyclo. Oh, this is not methyl, this is ethyl. So 1-ethyl cyclohexane, because you have 2 carbon chain over here. So the name is, or either you don't need to write 1, because if you don't write anything, we are assuming this is on the first carbon. So it's up to you whether you can write 1, or if you don't want to write 1 is also okay. So the name will be ethyl cyclohexane. So let's try to solve a couple of problems on this. So if you have this cycloalkane, how are you going to name it? So we know this is cyclopropane, and then these two things are substituent. So we have to start counting from the carbon that has the substituent. So I can start from this as number 1 or this as number 1. So it doesn't matter because both has methyl group as your substituent. If you would have something else instead of methyl, if you would have, let's imagine if you would have ethyl. If you would have ethyl, then you have to give the priority alphabetically. Then you have to start counting the carbon from this carbon. So we'll do one more example. So let's forget about ethyl right now. So it's up to you whether you start carbon 1, then you have to give the priority 2 and then 3. So make sure after writing 1 you cannot go over here and then write 2 on this carbon. Why? Because you have to give the priority to the second substituent. Always give the priority. So I can write the name as 1, 2, because 1 and 2 has the substituent and both substituents are same. Dimethyl cyclo, then the parent name, propane. So this is one example. Let's try the second example. You have 1. Now this is your second example. How you name this organic compound, this cyclo compound. So if you see over here, you have 2 substituents. This is your cyclo compound, which is cyclopentane. We have 5 carbon, 1, 2, 3, 4, 5. So this is your parent chain. Now we have to see which carbon we have to start with as number 1 carbon. So now you have 2 substituents. This is substituent number 1, which is ethyl. This is another substituent, which is methyl. So now we have to pick which carbon on the cyclopentane we have to put 1. So you have to write alphabetically. If you have 2 substituents, then you have to write alphabetically. So you have to, E comes first before M. So you have to write 1 over here, then 2, then give the lowest priority to the second substituent, then 4, then 5. So the name will be 1 ethyl, 3 methyl, then cyclopentane. So this is the IUPAC name, 1 ethyl, 3 methyl, cyclopentane. Let me give you one more example. If you have same cyclopentane, 5 carbon, and on one carbon you have chlorine, another carbon you have methyl group, CS3 group. So how are you going to solve this one? So again, we know the parent chain is cyclopentane. This is 5 carbon cyclo compound. So we know the name is cyclopentane. Now the problem is which carbon we have to start counting as number 1. So either I can choose this carbon as number 1 or this carbon as number 1. So again, both the substituent you have to use the alphabetical rule. Whichever the substituent comes first in alphabetically name, you have to put that substituent as your priority and then put the carbon that contain that substituent as number 1 carbon. So chlorine, this is your chloro, this is methyl. So C comes before M, methyl, so you have to write 1 over here, then 2, 3, 4, 5. So the name will be 1 chloro, 3 methyl, cyclopentane. So these are a couple of examples that you can use and then practice more example. So this is just an overview how you name any cyclo compound. Now let's talk about the isomerism. We already talked about the isomerism in the previous slide, but now we're going to see how isomerism can be found in cycloalkane. So what is isomerism? Isomerism has same molecular formula but different structure or arrangement of atom, right? So if I ask you, let's say if you have this is a cyclo compound with this, which is cyclobutane. This is 4 carbon, 1, 2, 3, 4. So if I have to move carbon number 1 and carbon number 2, if I have to rotate it using this bond between carbon number and 2, can I rotate the carbon 1 and 2 without breaking other bonds? No, we cannot move, because if I move the carbon 1 and 2 or rotate along this axis, the other bond might break, because this is cyclic compound. So there's a strain. If you move, there's no free rotation like I have or like we have in other compound, open chain compound. If I move these two carbon, I can easily move 3 and 4. Why? Because there is no more carbon attached to this. They are free rotated carbon or excess. But over here they are all interconnected. So if I want to move carbon 1 and carbon 2, there's a high chance we're gonna break one of these bonds. So it's not possible. So the free rotation is not possible in cycloalkane. So because of this, we're going to learn about a special isomerism called stereoisomerism. What is stereoisomers? Those compounds with the same structural formula, same molecular formula, but different spatial arrangement of atom. Means the connectivity of atom will be the same. So the bond is not going to break and then the carbon atom is not going to go and attach somewhere else. The connectivity of atom will be the same, but the spatial arrangement is different. Is different. So we're gonna learn what is spatial arrangement. So let's take an example over here. So let me rub this thing. So let's say if I have this cyclobutane again, if I have a compound A, a substituent A attached to it, substituent B attached to it, right? So let's imagine you have two substituents attached to this cyclobutane. If I want to move this carbon and move this atom A upward, right now is like downward. If I have to move upward, is it possible without breaking any of the bond? No. But if I have another compound that has A on the top and B on the bottom, so even though the bond between A and carbon is same, this A is attached to the same carbon like you have in the previous structure. The bonding is not changed, it's not broken. So let's number this one. 1, 2, 3, 4. 1, 2, 3, 4. So it's still A is attached to carbon number 2 like we have in the first structure, same as carbon number 1 is attached to B, carbon number attached to B, but now the spatial arrangement, the three-dimensional arrangement is changed. Right now A is on the top above the plane. This is now is above the plane, but in the previous structure number 1, the A is like below the plane. So this is the spatial arrangement. Means in 3 dimension you are just putting the atoms above or below the plane. That's it. So this is called stereoisomers, right? So let me tell you one more time. Stereoisomers have same molecular formula, same structural formula, but different arrangement of atom. In space or 3D space, right? So one of the type of stereoisomer is geometrical isomerism. So what is geometrical isomerism? So those compound or molecule will show geometrical isomer, those that have restricted rotation around a cis single bond. So those compound that cannot rotate around a single bond can show a geometric isomer. For example, cis and trans isomer. So we're gonna see how we're going to differentiate cis and trans isomer for geometric isomer. So, and for any di-substituted cycloalkane, what is di-substituted? Di means you have two substituent attached to the cycloalkane. Must be bound to groups at two different carbon of the ring. So that means if you have two substituent attached to the cycloalkane, both of them doesn't have to bind to the same carbon. It has to bind to two different carbon on the cycloalkane. That is very important. Two different. So we're gonna see one example that will help you to learn about this geometrical isomer, which is cis and trans isomer. So cis means both the substituent is on the same side. Whatever the substituent is attached is on the. So this is the same concept that I just explained. In open chain hydrocarbon or alkane, there is a free rotation, you can rotate it, but in a cycloalkane you cannot rotate it. It's not possible. That's why you have a stereoisomerism. So let's take this example of geometrical isomer, which is a type of stereoisomer. So this is a cyclopentane, right? And you have, this is carbon number 1, carbon number 2. This is again carbon number 1, carbon number 2. They have same name, 1,2-dimethyl, 1,2-dimethyl cyclopentane. So the structure is same naming, there is no difference in the structure. This is cyclopentane. On the first and second carbon you have the methyl substituent. On the first carbon, second carbon you have methyl substituent. But what's the difference between the two structure? In the first structure, both the substituent is below the plane, is on the same side. That's why we call as cis, because both is on the bottom. On the other structure, both the substituent is on the opposite side. You see, if this is the line, one is below the plane and another substituent is above the plane. So that's why we have trans. So because we cannot move this bond between carbon number 1 and 2, if we cannot rotate, then this CH3 molecule is not possible to go up, or this cannot go down. So this means these two structure are different. Right, so they are stereoisomers. So let me give you a couple of examples of cis and trans isomer for cycloalkane. So this is cyclobutane, and then if I put, so let me, okay, so let's say this is cyclobutane, and then on this one, this is one of the methyl group attached to this carbon, another methyl group attached to the same carbon but in the bottom. So is it possible to have a cis and trans isomer for this particular structure? No. Why? Because the rule to make a cis and trans isomer is both the substituent doesn't have to be connected or should not be connected to the same carbon of the cycloalkane. In this case, both the substituent is attached to the same carbon. So it's not possible to make a cis and trans isomer. But if one of the substituent would have attached from here, if it was like this, then it's possible to have a cis and trans isomer, because this, which kind of isomer is this one? This is trans isomer. which is what? Geometric cis and trans isomer, which is geometric isomer, right? Because geometry is different, right? If you have same structure but one CH3 is over here, second group substituent is on the second carbon, not on the same thing, then this is a cis isomer, right? Because they are on the same side. Over here they are on the opposite side, that's why it's trans isomer, right? And this is not possible for the first one because both the substituent is present on the same carbon, so it's not possible. So keep this in mind if you find any question regarding this, so make sure you know what's the cis and trans isomer. Now let's talk about the properties of the alkane. So we already know that alkane is being used for different purposes, right? We already talk about we have waxy coating on fruit, right? We use as fuel, but let's talk about what are the uses of alkane. So we all know the alkane with 1 to 4 carbon atom are gas at room temperature, and they are widely used as heating fuels like methane, ethane, propane. Alkane with a 5 to 8 carbons are normally being used as a fuel, right? Like pentane, hexane, heptane. And alkane with 9 to 17 carbon with a long chain carbon is normally used as a motor oil, mineral oil, kerosene or jet fuels, right? So we have many examples or many uses of different alkane depending on the length of the alkane. Now let's talk about the solubility and density of the alkane. Alkenes are non-polar because they are organic compound. If this is non-polar, this should be insoluble in water. So alkanes or mostly organic compounds are insoluble in water, most of the organic compound. They are less dense in water, they are flammable in air, and they found in crude oil. So you would have already seen in a couple of news, or you would have already or might have already seen in your on the sea, that if you have an oil spill on the ocean, then you will see some oil is floating on the top of the ocean and forming a thin layer on the surface. They are not dissolving or mixing with the water because they are insoluble in water. That's why we have oil spill, right? So now let's talk about the reaction of the alkane. What's the chemical reaction? Alkane normally do a combustion. What is combustion? In combustion, alkane react with oxygen, in the presence of oxygen, to give carbon dioxide and water, and along with energy, and this energy is being utilized for various purposes. So methane is a natural gas which is an alkane and which is used to cook our food on gas cooktop and to heat our homes, because of this energy being released during combustion and this energy being used to cook our food, heat our homes. So that's why combustion of alkane is important. Remember this thing, whenever you see what gonna be a product if you combust any alkane, then you're gonna produce carbon dioxide and water along with the energy. So make sure you know the product if you do combustion for any alkane in the presence of oxygen. Right. So before we finish this slide, I'm going to talk about a small topic called functional group that we're going to learn in the next slide or next chapter. What is functional group? Functional group is a unique reactive combination of atoms that differentiate molecule of organic compound of one class from another one. Means this is the combination of different atoms that when they combine together gives a spatial property for that particular compound. So let's say if O and H comes close together, they form an alcoholic group. If C and O come close together, C double bond O, they form an aldehyde. If oxygen comes between carbon and carbon, they form a special functional group called ether. So except alkane doesn't have any special functional group, except that each organic compound has at least one functional group that may be a multiple bond, either double or triple bond, or at least one oxygen and nitrogen atom. So let's see on this slide. So alkane doesn't have any functional group, but alkene has a functional group which is a double bond. Alkyne, triple bond, aromatic compound you have. We're gonna learn about this thing. Then alcohol, I already told you have OH group. Ether has this functional group COC. Then we're gonna learn about amine, which is NH2. You have nitrogen group attached to the organic compound. Aldehyde has C double bond O. Ketone has C double bond O2, but we're gonna learn what's the difference when we talk about aldehyde and ketone. Then we have carboxylic acid, C double bond OH, ester, C double bond OOC, and then amide is CONH2. So we're gonna learn each and every functional group when we talk about them, but this is just an overview that most of the organic compound contain this functional group, and then that normally change the property of that organic compound. So I'm gonna finish it here, and then from next slide we're gonna talk about our first functional group, which is alkene.